Good afternoon, Prof. We are Group 6 and in this video we'll be highlighting the importance of materials for aerospace through making comparisons between the materials used in planes and rockets. Airplane materials have evolved through 5 major stages. Early planes like the Wright Flyer used wood and fabric, which is light but fragile. In 1915, the Junkers J-1 introduced steel, proving all metal planes were possible. By the 1920s, aluminium alloys like the radium changed everything. It's strong, light and weather resistant, enabling aircraft like the DC-3, which made travelling globally practical. In the 1960s, titanium entered superjets like the SR-71. It handled the extreme heat of high-speed flight that aluminium couldn't. And today, carbon fiber composite dominates modern jet like Boeing 787. They are lighter, stronger, and more efficient, reducing fuel emissions.
Now moving on to the properties of airplane materials. First, airplane materials need to be lightweight. This helps reduce fuel consumption and improves the aircraft's overall performance. Next, they must have fatigue resistance, which means they can withstand repeated stress over time, especially during takeoff and landing. Another important property is high resistance to corrosion. Since airplanes are often exposed to moisture, chemicals, and salt air, corrosion resistance helps prevent weakening of the structure and ensure safety. We also have high strength-to-weight ratio. This means the materials are strong but still light, allowing for better efficiency and performance. Lastly, airplane materials must be able to withstand extreme temperature and pressure changes. This is crucial because airplane flies at high altitudes, where temperature and pressures vary greatly, especially near the jet engine.
Now, let's zoom into some examples. In 1992, an EIAI Boeing 747 crashed in Amsterdam after an engine broke off due to metal fatigue. The detached engine damaged the wing and control systems, causing the plane to lose control. In 1988, Aloha Airlines Flight 243 lost parts of its fuselage mid-air due to metal fatigue and corrosion. Years of repeated pressurization caused tiny cracks to grow, while Hawaii's salty, humid air sped up corrosion, eventually leading to the dramatic structural failure. These examples highlight the importance of picking the right material for the right vehicle.
Now let's talk about the materials used for airplanes. Titanium alloys are very strong and resist corrosion, used in wings and blades. Aluminum alloys are light and strong, used in the fuselage and wings. Magnesium alloys are the lightest metal and easy to shape. Super alloys can handle very high heat, used in jet engines. Ceramic composites are super strong and used in wings and engine parts. Ferrous alloys, like steel, are used for landing gear and frames. And finally, special fuels help airplanes fly safely at high altitude. This slide shows the plane composition breakdown. It illustrates the different material used to build an airplane and how each part is made from specific materials to balance strength, weight, and performance.
From the sturdy metals of the past to the advanced composites of today, the evolution of rocket materials is the story of space exploration itself. Let's take a quick journey through time. In the 1940s and 50s, we started with strong but heavy steel, quickly moving to lighter aluminum. The Apollo era pushed further, introducing titanium and nickel superalloys like Inconel for the incredible heat resistance in engines. The Space Shuttle brought us ceramics for thermal protection and carbon composites. Today, modern rockets use advanced aluminium-lithium alloys and carbon fiber. Interestingly, SpaceX Starship has brought back stainless steel for its strength at cryogenic temperatures and cost effectiveness. So, what makes a great rocket material? It's a balance of critical properties: high specific strength to reduce weight, thermal stability to survive extreme heat, and broadability for fabrication. They also need excellent cryogenic performance to handle liquid hydrogen and oxygen without becoming brittle, and corrosion resistance to withstand harsh environments from the factory to the launch pad. In short, the relentless pursuit of better materials, lighter, stronger, and more durable, is what ultimately powers our journey further into the solar system.
Next up, I'll be talking about the materials used for rockets. First material is aluminum alloy 2219, used in cryogenic propellant tanks, first stage tankage, and large welded panels for its high specific strength and excellent cryogenic toughness. Second material is aluminum alloy 2014, used in bulkheads, form sheets, and skin gore sheets for its high ambient strength, good machinability. Third material is super alloy, such as nickel and copper alloy, used in jet engines, blades, steels, and combustors, known for its outstanding high temperature strength and oxidation resistance. Fourth material is ablative TPS, insulating materials. Fifth material is stainless steel or high temperature steel, used in fittings, plumbing, and fasteners. Next, our sixth material will be cladding coating finishes to prevent corrosion and surface degradation. Seventh material are brazier solders and specialized joining materials to enable leak-tight and high-temperature joints. Eighth material are fasteners, small part alloys made of steel and titanium due to its strong corrosion resistance. And last but not least, our honeycomb sandwich panels and adhesives due to its excellent stiffness to weight ratio, used in areas needing high stiffness and low mass, like bulkheads and interstage panels.
I'll be doing a comparison analysis of rockets versus airplanes, focusing on how their materials differ and why. Both need to be light, strong, and corrosion resistant, so they often use similar materials. Things like aluminium, titanium, and composites keep them strong yet lightweight, but rockets face much harsher extremes. Airplanes see -50 to 40 degrees Celsius, while rockets go from -250 to over 1600 degrees Celsius under huge thrust. That's why rockets need styrogenic alloys and super alloys built for survival. In short, airplanes chase efficiency, rockets chase survival, and material size makes both possible. Thank you.